Now we're looking at section 4.3 about what derivatives tell us. So we already know that derivatives can be useful tools for finding critical points which are related to the local minima and maxima. We're going to further clarify how they are related in this section. Local minima and maxima are great for applications involving maximizing or minimizing, unsurprisingly, and yet derivatives, both first and second, tell us a great deal more about useful things about the behavior of the functions. Okay, before we begin, we're actually going to look at a little refresher from our pre-calc days, just some definitions here of increasing and decreasing functions. So first of all, suppose that a function f is defined on an interval. We say that f is increasing on the interval. We say that f is increasing on an interval if every subsequent y value is greater than the previous. So whenever you have a x2 value that is larger than an x1 value, the f of x2 value is larger than the f of x1 value. So for consecutive or subsequent x's, the y values are higher than the previous y values. That's the definition of increasing. And that's what they're stating right here in this notation. Okay, and for decreasing, we say that f is decreasing. Similarly, when you have subsequent x values that are larger than the previous, this time you want your subsequent y values to be lower than the previous. Those are the formal definitions of increasing and decreasing. So if we're going upward or downward are good metaphors for increasing and decreasing, and we provide that we always read the graph from left to right. So we have a function that's increasing. Again, you can see in the illustration here that whenever x2 is larger than x1, f of x2 is larger than f of x1. And for decreasing, whenever x2 is again larger than x1, this time for decreasing, f of x2, the y value is lower than the y value for f of x1. Those are the definitions for increasing and decreasing from pre-calc. So, the bottom of the page, we're looking at using a graph here to find the largest open intervals in which a function is increasing and decreasing. These intervals will always be open because at the changing points, you can't be increasing or decreasing, you're changing between the two, so you're doing neither. So we are going to use open intervals here. And if I want to list the intervals of increase and decrease, look at increase first. So we are increasing between, again, these are locations, so it's going to be between the x values, not the y values. So we're going to make a note of this. Where is going to be x values, indicating we're looking at where it's increasing. So it's increasing between 0 and 6, open interval. And it's also increasing a little bit later. So it decreases for a while. It also increases for a little bit later. Looks like between 8 and 9. All right. And then we can do our intervals of decrease. So we are decreasing between 6 and 8 and also 9 and 10. So increasing between 6 and 8. Also decreasing between 9 and 10. Now we're going to assume that this graph stops at the end of this grid for right now. We're not looking at continuing on, looking at infinite intervals. That way I can talk about the interval, the largest open interval over which we are decreasing. Okay, so the largest interval, which of these two intervals is larger? Okay, now remember that these intervals are x values, so we're looking at larger in terms of width of the intervals. So the first interval has a width of 2, and the second interval has a width of only 1. So even though I decreased in fewer y values, that's the larger of the two intervals. Okay, so the largest interval of decrease is from 6 to 8. So it decreased for the longest, even though it didn't decrease as low. It decreased for the longest time, if x was time, for example. So it's the widest interval. Okay. These intervals are x values, so I talk about them in terms of large and small based on how wide the x values are. All right. Let's take a look at the next page. Now we're going to look at some calculus definitions about increasing and decreasing. Okay. So we just started with the pre-calc definition. Here we go. So suppose that f is continuous on the interval I and differentiable. So just making a note of those two conditions. We saw those conditions play out plain in the last two sections. It's continuous and differentiable. And suppose that the derivative f prime is greater than 0. So if the derivative is greater than 0, that's going to mean slopes positive. So if your slopes are positive, then f, the original function, is increasing. Okay, that shouldn't be surprising since we already used that as a qualitative approach to understanding graphs from functions to derivatives. Now we're looking at them just in terms of the derivative. Similarly, if the derivative is less than 0, that means that the slope is negative, then your function is going to be decreasing. Then f is decreasing. So the sign, whether it's positive or negative, greater than 0 or less than 0 of the derivative, tells us something about the original function. Okay? This theorem relies on a familiar derivative is slope relationship that we definitely discussed in Chapter 3. Now we can make good use of the derivative to help us learn even more about functions. Anywhere a function switches from increasing to decreasing, okay? So if I'm switching, again, we're assuming that these functions are continuous and differentiable, so that's going to be important right here. If we have a continuous and differentiable function that switches from increasing to decreasing, then it's going to have to go through, to get from positive slope to a negative slope, it's going to have a maximum. It's going to have to go through 0. So my tangents are getting smaller and smaller and smaller until I reach that horizontal tangent, and then they start decreasing and getting larger negative. Okay. Same thing is going to be true if I switch from decreasing to increasing. We have those negatives and those positives. The only way to go from a negative to a positive is passing through 0 as long as we're in a continuous differentiable situation. So we have that horizontal tangent in the middle. And so we are able to determine, based on the way that we switch, what kind of extrema we have. So if I switch from increasing going up to decreasing going down, we have specifically a maximum. And if we switch from decreasing going down to increasing going up, we have specifically a minimum. So not just that we switch, but in which way we switch classifies the extrema as maximum or minimum. This is going to be our first way of classifying extrema based on how the function's derivative behaves around a critical value.